Welcome back to Learn Physics. In this video, we will see the effect of adding dielectric in between the plates of capacitor. Okay. So first, let us consider a simple parallel plate capacitor. The left side plate is positively charged and right side plate is negatively charged. So the charge density on the positive side is sigma and negative side is minus sigma. Okay. Now the distance between the two plates is d. So because of the charge there will be an electric field. That electric field from positive to negative plate, it is given by E0. So E0 is the electric field between the two plates, and the potential difference between the two plates is given by V0. Now we are going to substitute the values using the regular formula. The electric field between the plates is given by sigma times epsilon naught. Okay, this formula is the result of Gauss law in the first chapter. The electric field due to the first plate is given by sigma by 2 times epsilon naught. For second plate it is negative, the field will move towards it, so this is also sigma by 2 epsilon naught. If you add them together you will get this result. Okay, so I'm just erasing this. Now the potential difference between the plates V0, that is given by E0 times the gap between the two plates. So using the value of electric field in this, so we will get sigma by epsilon naught times d. Okay, and also we know the value of sigma is nothing but amount of charge contained per unit area. So instead of sigma we can replace that with q by a. So a times epsilon naught, this is the value of V naught. And capacitance formula, we know that, right? The capacitance bit of the plate is C naught, it is given by Q divided by V naught. Okay, using the Q as it is, replacing the value of V naught here, so we will get QD divided by A times epsilon naught. Okay, and then we can cancel the Q and Q, we will be left with A times epsilon naught divided by D. So this gives the capacitance of a parallel plate capacitor when vacuum is the medium between the plates. So we can note this as equation 1. Okay, if the medium between the two plates is vacuum, this is what the actual capacitance. Okay, now what we are going to do is we are going to keep a dielectric material between the two plates. Okay, so let me redraw the diagram. Now we are going to place a dielectric in between the two parallel plates. This is the positively charged plate and this is negatively charged plate. Okay, so let me place a dielectric in this. Thus the yellow color line indicates the dielectric material which is tightly placed between the two plates of capacitor without leaving any air gap. We know that whenever some electric dipoles like this are randomly kept in external electric field, okay, so these dipoles will redirect themselves so that it is completely aligned with the applied electric field. The same thing happens here also. The dipoles which is inside the dielectric will align themselves along the direction of the electric field between the plates. You can see clearly the positive end of one dipole stays closer to the negative end of another dipole. So this will make the net charge inside the dielectric into 0. So we only left with the negative charges on the left side and the positive charges on the right side. So this charge has a charge density of minus sigma p, and this is with the charge density plus sigma p. So sigma p indicates the charge which are created due to the polarization. That's why letter p is used. Already we have a charge density on the plate, positive sigma, and the negative it is minus sigma. Now the plate will look like this. On the left side you can see you will be left with sigma minus sigma p. So I'm just added the two charge densities. Okay, so the one is due to the charged plate and another one is due to the induced charges in the dipole. Clear? The right side also we have the same, just add them together, we will get minus sigma plus sigma p. If negative sign is taken out, we will be left with sigma minus sigma p. So the charge on the right side is sigma minus sigma p, and the charge on the left side is negative of sigma minus sigma p. Okay. Now we are going to find the capacitance of this setup. We can see one side we have sigma minus sigma p, and another side we have negative of sigma minus sigma p. So we can compare this with our previous case. Okay, so if the left plate has the positive charge and right one has something negative charge, the electric field between them is given by E is equal to sigma by epsilon naught. Okay, so in the same way, the electric field between these two plates is given by, you have sigma minus sigma p divided by epsilon naught, right? Clear? So in the first case we have sigma, so I used a sigma. In this case we have sigma minus sigma p, so I used that value in the numerator. Clear? Now, and the potential difference between the plates is given by V is equal to E times D. We know the formula, and I'm using the E value in this. I will get sigma minus sigma p divided by epsilon naught times D. This is the potential difference between the plates. We know that sigma p is actually an induced charge. Sigma p is induced charge density because of the applied charges on the plate. Sigma is the charge which lies on the plate, which is marked in the white color. Okay, and sigma p is the induced charge. If the sigma increases, the electric field between the plate increases. If the sigma value increases, the electric field between the plate increases, which in turn increases the polarization, and the induced charge will also increase. So we can say the sigma p is directly proportional to the sigma. We are so clear that if sigma value is doubled, sigma p will also doubled. If you subtract the sigma from sigma p, their difference will also get doubled. Clear? If sigma is doubled, which in turn increases the sigma p, this is also get doubled, so the difference between the sigma and sigma p will also double. So we can directly say sigma minus sigma p is proportional to sigma. I'm telling this again. Sigma p is completely dependent on sigma. When the sigma increases, which is the charges on the plate increases, which in turn increases the polarization, this increased polarization result in the increased induced charges in the dielectric. So if sigma doubles, sigma p will also double, then the difference between the sigma and sigma p will also double. So we can see whenever the sigma doubles, the difference between the sigma and sigma p will also get doubled. Okay, to remove the proportionality symbol, so I'm going to replace this with the proportionality constant, that is 1 by k. Here the k is called a dielectric constant. Its formula is given by epsilon divided by epsilon naught. It is the ratio of the permittivity of the given dielectric medium to the permittivity of the free space. Just rearrange, so you will get k is equal to sigma divided by sigma minus sigma p. So you can check the numerator value is greater than the denominator. Okay, so here the numerator value is much greater than denominator, so the result of division is always greater than 1. So we can conclude that the k value is always greater than 1. We will use this in the derivation again. Instead of sigma minus sigma p, we can use this relation here. So in the V, initially we had sigma minus sigma p into d divided by epsilon naught. So sigma minus sigma p into d divided by epsilon naught. So from this we can write sigma minus sigma p value as sigma by k. Putting this here, so I will get sigma by k times epsilon naught d. Okay, and the capacitance between the two plates is given by q by v. Q, you can keep the q as it is. For v, we should replace sigma k epsilon naught times d. We know that q can be replaced with sigma times a, so we will be left with sigma k epsilon naught times d. Sigma and sigma will get cancelled. We will be left with k times a epsilon naught divided by d. This is the new C value after the dielectric is inserted between the plates. We can take this as equation 2. In the first case, we have the equation C naught value is A times epsilon naught D. So I'm just writing it here. Before the dielectric was kept, the capacitance value is A times epsilon naught D. So after inserting a dielectric, the new capacitance value is actually multiplied by a factor called K. So we know that we have already seen that the value of K is always greater than 1. Okay, so if C naught is multiplied with a number which is greater than 1, its value, the result is always higher than the C naught. So we can conclude that if a dielectric is added, the capacitance of the capacitor will increase by a factor of K, right?